Collision theory, the chemical theory of car accidents. No, I'm just kidding. Or am I? Let's get started. All right, based on the collision model, you're going to need three things in order for a reaction to happen. In order for it to happen, you have to first, the molecules must collide, and they must collide with enough energy to get something to happen. We can't have any lazy molecules. And the third thing is that the molecules must collide at the right orientation. All right, what do I mean by orientation? I'd like to introduce you to my two friends here. This is Clyde. Say hello, Clyde. Hi. And this is my friend Ida, and she's way chipper. Hi. Okay, so Clyde and Ida here are going to demonstrate collision theory. So these are molecules, and molecules have little electrons around them. And then sometimes part of the molecule you can't bond with it. It doesn't have an activation site or a bonding site. So Clyde here only has this small little area right here to bond with. Ida has lots of electrons, and here she has open space. She has open space to bond with Clyde. So if everything works out and they're moving they're moving really fast, and the electrons bond right there, and we get, boom, a collision, and it happens with enough force, then we get a reaction. If Clyde and Ida are not facing the right orientation and a collision happens, boom, there's nothing here on that side of Ida, and there's nothing here on that side of Clyde to bond. So then we don't get a reaction. So activation energy, the energy required for a reaction to occur, is essentially what we're going to measure in this video, okay? And we measure that through reaction coordinate diagrams. I'm going to draw two reaction coordinate diagrams here. Here I have two reaction coordinate diagrams. On the left-hand side, this is just potential energy. And then this, you can consider the x-axis, just over time. And so basically this shows how energy inside of the system, container, cell, whatever system we're talking about here, changes during an actual reaction. So the potential energy comes in one side here and goes through a system and a process, and the products come out the other side. Now there's two basic different types of reaction coordinate diagrams. These two diagrams, the names may sound familiar. The first one is endothermic, and the second one is exothermic. And I remember these two diagrams by exothermic, meaning exit, energy is released here, and endo, like I'm going in the dough of the house. Energy is absorbed. It's going into the reaction. In the dough, endothermic. And exothermic, we have a release of energy. Both of these diagrams show activation energy. Activation energy is the energy from here to here. And on the other diagram, it's the energy level from here to here. That is abbreviated by EA, activation energy. So activation energy is essentially from where the reactants are to the top of the hill. Now the change in energy from where the reactants are to where the products end up is what we call change in H. Or that's the actual change in energy. And we have a fancy word for that, and we call that enthalpy. And enthalpy describes basically the change in energy from where the reactants to the products are. And so change in H on our endo in the dough reaction coordinate diagram is right here. This is change in H from reactants to products. This measurement is our enthalpy. And from this whole part right here, from reactants to the top of the hill, that is EA, activation energy. Okay, so we're talking about reactions happening like inside of a container, molecules colliding together, and how can we make that happen faster? And you just have to influence it. You have to help along, help along the reaction. You can make the molecules collide more often, and with more energy, and that'll make the reaction go faster. If you take energy out of the system and the molecules collide less frequently, then you'll make the reaction slower, so you can influence it on the slower side. So how do these other factors affect the collision of molecules, like concentration, for example? Concentration is actually the amount of molecules inside of the container. I can add more molecules inside the container, and if I add more molecules, then I increase the amount, which is going to then increase my chances of collision. Yeah, collision. COLLISION. Okay, that's going to increase my chances. All right? It's like, you know what? I'm not going to talk about increasing your chances. We'll just move on. All right, moving on. Other things that we can do to influence the reaction. Well, we could change the temperature. All right. If I increase the temperature, then I basically increase the kinetic energy, right? The overall energy inside of the system. When I increase the energy, I make stuff move faster. And so when I make them move faster, they have greater chances of colliding. Okay, particle size and surface area. All right, here comes Clyde and Ida again. Clyde wants to collide with this situation and this situation. Ida has more surface area right here, and the molecule Ida inside of this container, Clyde can only go that way. She has less surface area. So the availability for them to collide is greater over here than it is over here. So Clyde can have better chances of making a reaction happen with Ida as he collides on this greater surface area. Clyde over here doesn't have as many chances to collide with Ida because the amount of exposed Ida molecule right here is less. So if I increase the surface area, I increase the rate at which things happen. All right, pressure. Pressure is defined as the collision of the molecules against the side of the container. For our purposes, and when we're talking about collision theory and how reactions occur and the rate at which they occur, we're really talking about volume of where the molecules are getting to move around. All right, so let me draw Clyde and Ida again. So in my example number 1, here's the lid on my container, and there's a great volume here for Clyde and Ida. See, they have lots of space to move around. I decreased the pressure and I gave them more volume, and so they have more space to move around. So the chances of them colliding are not as great than if I increase the pressure, and if I increase the pressure and I squash them and I put them in a smaller volume in a smaller space, then they're more likely to collide with enough energy in the right orientation to get the reaction to occur. So if I increase the pressure, like over here, I increase the pressure And so I'm decreasing the volume, then I'm going to increase the rate at which Ida and Clyde will collide. A catalyst. So what is a catalyst? Because it's not a record of all the cows you own. A catalyst makes reactions require less energy. So here I have my exothermic reaction coordinate diagram here. And then if I were going to have a catalyst, it would kind of do this. See how my activation energy is from here to here on the normal reaction, but from here to here on the catalyst. The catalyst that I added to this reaction is making it require less energy. The results are ultimately the same, and the catalyst doesn't influence the reaction like what's going on in the container. It just kind of helps it along a little bit. So, to draw it a little better, in a reaction coordinate diagram, you have your normal reactants and then products. And this is our normal reaction. And when I add a catalyst, I just change the activation energy and I make the reaction require less energy to occur.